All right. So the most important thing in cluster sampling is that we need to know about the notations. So the notation that we have been using are quite somehow it is quite different in the cluster sampling chapter. Okay, so imagine, go back to our, rewind a little bit. In cluster sampling, that we have, imagine that we have a population, and then we divide the population into different clusters. And then we randomly choose some of the cluster to be included in our sample. So what we are focusing would be more of the cluster calculation or the cluster data that we collected. Okay, so in the notations, first of all, in section 6.3, we can see that capital N is indeed the number of clusters in the population. So for example, if we are interested in the population, we divide them into different clusters. So how many clusters would be capital N in total? And then we select how many clusters into our sample would become our little n. Okay, and when we talk about that, when we refer back to the previous sampling scheme, that we are more focusing on the element or each of the individuals within the cluster sampling, we look at M. That's just the little m to indicate how many of those elements in each of the cluster. So for example, mi will indicate for each of the cluster how many elements or how many individuals is within particular cluster. So if for example we have one cluster 1 all the way up to the total number of cluster in the populations, so mi indicates how many elements within each of the cluster. So if we add up the total number of elements for each of the cluster, if we add it from I going from 1 to little n, that is the total number of cluster in our sample, and then divided by the number of samples, so we are actually estimating the average size of the cluster in our sample. Okay, so secondly, if we look at the total number of elements in the population, so actually we are adding up the number of elements in each of the cluster, but we are looking into the total number of clusters in the population for the summation. So capital M would indeed be the number of elements in population. And if we divide the total number of elements in the population by the total number of clusters in the population, so we're getting the average size of the cluster. So we have a capital M bar. So if I'm trying to be, I don't want to be too confusing, but if you just think about that, the capital M, the total number of elements in the population, is quite similar to the capital N in simple random sampling or stratified random samplings, that we're looking at how many elements in the population. But now in cluster sampling, we are more focusing on the clusters numbers. Okay. Yi again would be the Y total for the cluster. So we are looking at a collective cluster total. Okay, so Yi would be the sum of all of the elements variables to have the Yi. So in other words, within a particular cluster, so let's say within a cluster cluster I, J could go from 1 to the size of the cluster Mi. Okay, so Yij is indeed referring to each of the elements within the cluster. All right, so we come to section 6.4 on the estimation of the total of the population mean. Okay, we can again use cluster sampling to estimate the population mean. How we do that? First of all, we have different approaches. First one is called the ratio estimation. The ratio estimation for the per capita average is using the Y bar, that's a double bar, to indicate this is the mean of mean, right? So we have the custom means for each individual. So in that case, we add up all of the cluster total, which is Yi, and the cluster total add up from the first cluster up to the little n cluster within our sample. So this is actually adding up all of the individual for each of the cluster and up to the total number of cluster in the sample, and divided by the cluster size and for the total cluster size for all of the elements in the sample. So in other words, the mean would be estimated by the summation of yi divided by summation of mi, and the estimated variance is equals to 1 over capital M bar square multiplied to the finite population correction factor times SR square over n. So if you look at this equation, they're quite somehow you may find it quite familiar, because we have like a SR square in the estimated variance. So we are actually looking this approach similar to the ratio estimation in chapter 3 in a simple random sampling. Okay, so let's go back. This is chapter 3 in simple random sampling under the ratio estimation. Remember in chapter 3 we said that we can estimate R from our sample, which is dividing the summation of yi divided by summation of xi. And we can say that R would be the unbiased estimator for the population R. And we have the variance estimate. Let's use the equation 3.25. The variance for my ratio estimation is 1 over mu x squared, which is capital X bar square, multiplied to the finite population correction vector, multiplied to SR square over n. So compare this to, we are actually looking at the same thing. So y double bar is indeed the ratio estimator of comparing the summation of yi divided by summation of mi, but in simple random sampling that would be xi. Okay, and then the estimated variance is indeed the finite population correction factor multiplied to SR square over n divided by the true value of x bar square, or the true value of our average cluster size in the population, capital M bar square. Okay, so if you compare the formula, it is indeed the same. So that's why we call the first estimator for the mean is the ratio estimation. So with this estimation, or with this approach, is generally share the same characteristics like the ratio estimation that we use in simple random sampling. First of all, the remarks, our y bar mean takes the form of the ratio estimator as developed in chapter 3, with mi taking the place of xi. If m is unknown, then we don't have m bar, so we don't have, assuming that we don't have the average cluster size in the population, we can estimate it by our average size of the cluster in our sample. Thirdly, the estimated variance in equation 6.2 is biased, just like how we treated previously in the ratio estimation. So we can say it is still a good estimator if n is large enough. In this case, n is the number of clusters that we are sampling. Fourthly, the bias of the estimated variance would disappear if the cluster size are all equal. So if we have M1, M2, and up to our cluster n in the population, if they're all equal, then the estimated variance would be unbiased. We can look into this kind of special case for the equal size cluster later on. And finally, as in all cases in ratio estimation, we can find a fitted weighted regression line. If that fitted line passed through the origins, we can also say the ratio estimator is unbiased estimator. Okay, so this is the first approach within the one-stage cluster sampling using the ratio estimation. So let's look at an example previously, that the interviews are conducted in each of the 25 blocks sample in example 6.1, and then we collect the data of the cluster total income. Okay, so we're not looking at each individual, we're looking at yi, the cluster total income. And then we also know that within a cluster, how many residents are there. So they are unequal cluster size, but we also obtain the total yi. Okay, so using the ratio estimation or ratio approach, we can estimate the population by the ratio estimator. So we add up the total of the cluster total divided by the total of the cluster size. So we're actually looking at 151 individuals, and then the total income for everyone in the cluster in our sample is 1,329,000. So on average, per capita income is around 8,801. And in this case, we don't have the total population number, so we don't know what's the average cluster size in the population, but again, we can estimate the average cluster size within our sample. So we have 151 in total of the individuals out of the 25 clusters. So on average, the size or the cluster size is around 6.04. And we also know that capital N is 415 cluster in total in the population. So we can estimate all this and plug that into the formula for the estimated variance. Okay. Again, we should be able to calculate the SR square, like the ratio estimator. We can find the SR square using the formula. It is equals to 25189, and divided by the, again, N is the number of clusters that we sample, and then N out of the total number of clusters in the population. Taking a square root of the variance multiplied to the final constant at the 95% confidence level. So we have the confidence interval was expected. Secondly, example 6.3, a company provides its salesmen with cars for work-related traveling. So there are in total 810 cars, 12 branches, but we only sample 4 branches. So we have capital N equals 12, but we only sample 4 of them. 810 is the total number of cars in the entire company. So the capital M is 810. Again, look at the 4 branches that we sample. We have the total mileage for each of the branch. And within each of the branch, we also know how many cars we have, right? So we can estimate, again, the mean number of cars per branch for the population. So 810 cars out of 12 branches. So on average, each branch would have about 67.5 cars. The mean mileage per branch would be the total of the mileage that we run divided by how many branches that we sample. So on average, it's about 1,585. Mean mileage per car would be the total mileage divided by the total number of cars in all these branches that we sample. So that would be 240. So that's around 26.42. Okay, so in this example, it is very much similar to example 6.3, but we can use the ratio estimation approach like how we did previously. So we have MI, YI, and then we have YI minus MI Y bar. So it's similar to the previous table that we used is YI minus RXI. Take a square and look at the sum. So this would become, if we use this value divided by n minus 1, is indeed the SR square. Okay, so we can substitute this SR square into the estimated variance of my ratio estimator. So this is around 0.441.